Radioactive decay. Now, radioactive substances decay by spontaneously emitting radiation. If m of t is the mass remaining from an initial mass, m naught, of the substance after time t, then the radioactive decay rate is going to equal negative 1 over m dm over dt, and has been found experimentally to be constant. Since dm over dt is negative, the relative decay rate is positive. So it follows that dm over dt is equal to k times m, where k is a negative constant. So in other words, radioactive substances decay at a rate proportional to the remaining mass. So this means that we can use equation 2 to show that the mass decays exponentially. So m of t is going to equal the initial mass times e to the power of the constant k times time t. Now, physicists express the rate of decay in terms of half-life, the time required for half of any given quantity to decay. Now, in example 3, the half-life of radium-226 is 1,590 years. In part A sample of radium-226 has a mass of 100 milligrams. We want to find the formula for the mass of 2688 radium that remains after T years. So in part A, what we're going to do is we're going to let m of t be the mass of the radium-226 in milligrams that remains after T years. Then dm over dt is going to equal the constant k times m, the mass, and the initial would then be at 0. Then we know that it's going to have a mass of 100 milligrams. So now using equation 2, m of t is going to equal m of 0 e to the k times t. So m of t is m of 0, which was 100. So we're going to get m of t, which is equal to 100 e to the power of k times t. Now, in order to determine the value of k, we have to use the fact that the year, which is 1590 years, is equal to 1/2 of 100. Thus, 100 e to the 1590k is going to equal 50. And so in order to solve for the value of k, I know they solved that over here, but I'm going to show you what happens algebraically to the right. So we have our equation 100 e to the 1590k, which is equal to 50. We're going to divide both sides by 100, and then we get 1/2. And then taking the natural log of both sides. And then we're going to get 1590k. Now over here, what they do is they separate the natural log of 1/2 using the subtraction property. So you're going to get the natural log of 1 minus the natural log of 2. And so the natural log of 1 becomes 0, which is the reason why they get the negative natural log of 2. And then dividing both sides by 1590, then we get our constant k to be negative natural log of 2 divided by 1590. So therefore, there is our function. And we could also use the fact that e to the natural log of 2 is equal to 2 to write the expression for m of t in an alternative form, which would be m of t is equal to 100 times 2 to the negative t divided by 1590. Now in part B, we want to find the mass after 1,000 years correct to the nearest milligram. So we're going to use the formula that we got the first time. So the mass after 1,000 years is going to be the following. M at time t, which is 1,000. We're going to plug that in for t, and then follow the order of operations on your calculator to get approximately 65 milligrams. In part C, it says, when will the mass be reduced to 30 milligrams? So we want to find the value of t, meaning what would the time be when the mass has been reduced to 30 milligrams. So that is, we're taking the function and setting it equal to 30. And so now we can divide both sides by 100. So we're going to get e to the negative natural log of 2t divided by 1590, which is equal to 0.3. And then if we take the natural log of both sides, then we get negative natural log of 2 divided by 1590t, which is equal to the natural log of 0.3. And then we're going to multiply both sides by the reciprocal in front of t to solve for t. So we're going to get negative 1590 times the natural log of 0.3 divided by the natural log of 2, which is approximately 2,762 years. So the value of t for when the mass would be reduced to 30 milligrams is going to be 2,762 years. Now, if we want to check our work in example 3, we can use a graphing device to draw the graph of the function in figure 4 together with the horizontal line where m is equal to 30. And so where these curves intersect is approximately 2800, which is close to what we got for our approximation.